Good afternoon, everyone. My name is Breana. I'm on the developer relations team based here in New York City, and I work on the Android team. Today I'm going to be sharing a few best practices for background task execution using the APIs for deferrable work, which are WorkManager and JobScheduler. And since this is an introductory level talk, I'm going to begin with a brief overview of some of the history of the options for background work on Android. And I also want to stress that this is a very brief overview. So some of this history might actually already be familiar to you. Before Android 6, developers primarily relied on services, broadcast receivers, and alarms for background work. With the release of Android 6, Doze mode was introduced, and this impacted how apps could perform background tasks. If you're not familiar, Doze is a power-saving feature that defers background work and network activity when a device goes unused for periods of time. And this also meant that the previous solutions that I mentioned before weren't always reliable, which led to JobScheduler becoming the recommended way to perform tasks in the background in a way that was also optimized by the system. In Android 8, background execution limits were also introduced, which placed more restrictions on what apps could do while their users weren't actively interacting with the app. This also led to the recommendation of JobScheduler for deferrable work, and then for foreground services for user-perceptible work. In Android 9, there was another power-saving feature introduced, which was called App Standby Buckets. And these are categories or buckets that the system places you in based on how often your app is used on the device. And the system will also limit resources based on which app standby bucket your app is currently in. And this is also when WorkManager was introduced and became the recommended solution for deferrable background tasks. In Android 12, there were also restrictions that were introduced on launching a foreground service from the background, but they also had a few exceptions. And in Android 14, foreground service types were required, which made it so developers had to explicitly declare the purpose of their foreground service along with an associated permission. And so looking at all of these changes laid out and this continuous evolution of background work policies can definitely make it seem like the Android team is just placing layers upon layers of restrictions without any good reason to. But I can assure you that every one of these changes serves a vital purpose, and the team is balancing both user and developer needs. And I think that these kind of bubble up to three key areas that the team is prioritizing: increasing user control, enhancing transparency, mostly for users, and very importantly, improving battery life across the ecosystem. And almost every app has a reason to run tasks in the background, and this is why the Android team continues to improve the OS and also improve the APIs that are used for background tasks like WorkManager and like JobScheduler. So this talk will cover some of the nuances, some of the gotchas, and also maybe somewhat overlooked aspects of using these APIs, including how to choose the right API for your use case, and also very importantly, how to debug work when you aren't sure what went wrong. And since we're in New York, I thought it could be fun to walk through some of these best practices in a themed way. So I'm a huge Broadway fan. It is one of my favorite things about living here. I've seen 8 shows this year already, which is a record for me. And so I'm going to weave some best practices and tips and tricks into this talk while walking through a few features for a fictional all-in-one Broadway app that I wish existed. So here's a list of our app's key features. I won't read through all of them because there's a lot, but just to name a few: the ability to show ticket availability for a show, price drops and promos for specific seats that we're interested in, lottery results for specific shows. If you're not familiar, lotteries are daily drawings that shows have for discounted tickets. Typically, they happen twice a day. Once at 10, once at 3, which means you've missed the one for today, but if you want to enter tomorrow, once they release the results, you get an hour to purchase a ticket, and then the show is for the next day. So if you enter tomorrow and you're in New York on Friday, you could go. We'll also have the ability to favorite a show, and then a feature I'm really excited about is the ability to download a digital program, and you can reference it on your device offline. So, as I said, really long list of features. So we're only going to focus on 4 of these today. These are the digital program feature with offline download, the lottery results feature, and then also price drops and ticket availability, which I have combined into one because they're very similar in how they work. So without further ado, let's get started. Okay. So starting on our first feature, which is the digital program with offline download. So when a user opens the app and navigates to a show, we want them to see a digital program that contains all of the information about the show that they're about to see, which includes cast, crew, a synopsis, and a video. And this content will also be available to view offline, as I mentioned. Because there are a lot of shows that are currently available, we don't want to pre-populate this information in the app for every show. Instead, we want to give users the option to download the content for the specific show that they're interested in. So after clicking that green download button, the content will download and also be available for them to reference offline, which helps to save storage space since we're not saving every show. So this brings us to our first choice, which is what should we use for this scenario? And there are a few things that we need to consider when we're making this choice. When the user clicks download, I want a few things to happen. Number 1, we want the content to download reliably, and we also want to be able to support a download that'll take more than 10 minutes since we have a lot of high quality images. We also have that video that we mentioned. I also want to show a notification that informs the user that the download is in progress and then also lets them know when it's complete, because again, the action was user initiated and user requested, so we should let them know where we are on that download. We also only want the download to start if we're connected to a network, since there's no other way for us to get this content. We also want the download to continue if the user exits the app for whatever reason. And finally, if our download fails, the app should retry the download. So as I was listing these requirements, you might have already thought about one or even multiple ways that we can perform this work, with an emphasis on making sure that our work continues in the background. So these are some of the options that I thought of. One option is a foreground service. A foreground service is a way to asynchronously perform operations that are noticeable to the user. They're accompanied by a notification, and they're used for tasks that shouldn't be interrupted. So you've probably seen this when playing music or navigating somewhere. In terms of our requirements, though, foreground services only cleanly tick 3 of the 5 boxes. They don't have an associated network constraint, so this would require us to write some additional code. They also don't automatically retry this work in the event of a failure. Another option is WorkManager, which we briefly touched upon in the intro. And as a reminder, WorkManager is an Android Jetpack library that allows you to schedule and manage background tasks in a way that cooperates with the system. WorkManager was introduced as a way to schedule and run deferrable work, which is work that can run at a later time and doesn't need to run immediately. This has also changed since WorkManager was first introduced, but we'll get to that a bit later. So again, we'll get into the nuances of WorkManager in a bit, as well as support for long-running and expedited work. But for our requirements, a regular worker only cleanly ticks 4 of those 5 boxes. For a regular worker, if our work exceeds 10 minutes, then it will be rescheduled by the system. Finally, JobScheduler. This is an Android platform API that, like WorkManager, lets you schedule and manage background tasks in accordance with the system. Okay, so I have checked all the boxes for JobScheduler here. You might recall that WorkManager uses JobScheduler internally on Android 6 and up, but again, I didn't check all the boxes for WorkManager. I'm taking some liberties because we're going to use a very specific type of JobScheduler job here. So before we get into that, let's walk through some of the differences between WorkManager and JobScheduler, because they're very similar APIs, and a very common question that a lot of developers have is when should you choose to use one over the other? So WorkManager is generally recommended for most scenarios. It's a lot easier to use. It's a Jetpack library, so it reduces a lot of the boilerplate code that you would need to use a platform or framework library like JobScheduler. It also offers backwards compatibility down to Android 4 and abstracts away the device and the OS version differences. So you write your work once, and then WorkManager decides under the hood whether to use JobScheduler on certain versions, Alarm Manager on other versions, or a combination of things, depending on the OS version. There's also a number of super useful features that WorkManager has, like the ability to chain work, where one piece of work depends on the completion of another, and you can also pass the output of one worker to the next. And you can also run work in parallel. It also offers flexible retry policies for failed work, and also has a concept of expedited work where you can get a task scheduled immediately. So this is all really great, but there are also specific situations in which JobScheduler might be a better choice. So a couple examples of this. JobScheduler has a method called getPendingJobReasons, which is a way for you to get more insights into why a job hasn't been executed by the system. So that can be anything from your job's constraints not being met or additional constraints having been imposed by the system. It also offers a set prefetch method, which you can use to let the system know that the particular job that you want to run will be prefetching content. So the system uses this signal along with its knowledge of the user's usage patterns of the device and of the app to prefetch content before the app is opened. And finally, JobScheduler offers the set user initiated method, which is associated with a specific type of job called a user initiated data transfer. So now that we've laid all of these options out, we're going to go with option 3, which is JobScheduler, specifically because for this feature, we want to use the user-initiated data transfer. UIDT jobs were designed specifically for scenarios that have longer duration data transfers that are initiated by the user, work that ideally needs to start as the user requests it, operations that require a notification, again, because they're user requested, and also work that is subject to constraints. And the great thing about a user-initiated data transfer job is that the system will grant a higher priority and also resources once it knows that a job is user-initiated. And I also want to stress that the other two choices we had, foreground services and WorkManager, are still valid for performing downloads, but they're just not the best choice for our specific scenario. To cover some additional reasons for why we're choosing not to use a foreground service in this scenario, we mentioned that foreground services don't have a network constraint or this awareness of the network, whereas with UIDT, we can make sure that the job defers until the network constraint is met. There's also no minimal effort way for us to confirm that the task was completed if we use a foreground service, whereas with UIDT, because it is a JobScheduler job, we can call job finished to signal that the job was done successfully, and if it wasn't done successfully, then we can reschedule it. And the main reason for choosing to use UIDT again is this is more future-proof, and it's also the direction that the platform is heading and the recommended solution for developers, specifically for data transfers and downloads. So if you are familiar with WorkManager from using it, you might be thinking, what about WorkManager's set foreground method? Isn't that very similar to what we're trying to achieve here with a user-initiated data transfer? And if you're not familiar, WorkManager has a set foreground method, which can actually make a WorkManager worker run as a foreground service. So it'll show a notification, and it'll also gain that elevated priority that we get with UIDT. And this also allows for longer duration work. I mentioned earlier that one of the issues with using WorkManager is that if our download takes longer than 10 minutes, it'll be rescheduled. Set foreground means that the work can run longer than 10 minutes. However, while this does achieve a similar effect to UIDT, again, we're choosing it here because it's the dedicated API that's specifically designed and optimized at the system level for the high priority, user-initiated, long-running data transfers. So hopefully this isn't too much of a tangent, but if you are familiar with UIDT and you have used it, you might know that we actually do have to support both a UIDT implementation and a WorkManager implementation. So this is because UIDT does have a limitation where it only works for Android 14 and above. So to support other versions of Android, we will need to check for the OS version and then fall back to the WorkManager implementation where UIDT is not supported. So the recommendation, if you already have an existing WorkManager implementation for a download or a data transfer, is to maintain only that. But if you're starting from scratch like we are with our app, the recommendation is to support both. And again, the reason that we're primarily opting for a UIDT here and we want to support it is because it's the recommended solution for user-initiated data transfers. In most background task scenarios, though, WorkManager is probably the best choice. Okay, so let's walk through some code for this feature. So first, because this is a job scheduler job, we have to declare a job service in our app manifest. User-initiated data transfers also have a specific permission that needs to be declared, which is the run user-initiated jobs permission. For the actual logic of our download, we define digital program service, which extends job service. And the other important thing to note here is that we have to call set notification as well in order to provide JobScheduler with the notification that is associated with this data transfer. The notification should describe the work that's being done, as well as the associated progress. And if this method isn't called, then the job will actually be stopped by the system. And I didn't show it here, but because we're showing a notification, we also have to make sure that we request the post notifications permission. And as with any job scheduler job, we call job finished to let the system know that the job is complete or that it needs to be rescheduled. So if it needed to be rescheduled, we'd say true instead of false there. So now let's take a look at how we structure the actual job. When we build our job info object, we indicate that this is user initiated by calling the set user initiated method that I mentioned earlier. We've also called set required network, which is actually mandatory when scheduling a user-initiated data transfer job. And in our network request builder, we specified that we have to have an internet connection for this download. We've also estimated the payload size for this download. The set estimated network bytes supports both an upload estimate and a download estimate, but since we aren't uploading anything here, we've only specified that first value and left the upload at 0. And specifying this just helps the system to prioritize work. Okay, so that's the foundation for the digital program feature. Here's a quick recap of what we covered in this section: the differences between foreground services, WorkManager, and JobScheduler, when to choose WorkManager and when to choose JobScheduler, and how to create a JobScheduler UIDT job. So let's move on to our second feature, which is the lottery alerts feature. This feature will track our lottery wins and let us know how much time we have left to claim our tickets. For the specific show that was won, the app will have a countdown timer for the purchase, display some show-specific artwork, and when we need to be notified about our win, it'll also load this show art and display it in a notification that will let us know that it's time to buy our tickets. So there are a few things here that we know will inform our choice as well. Number one, we only have an hour to purchase the tickets before they're offered to someone else. So we need to make sure that we're informed of these results within the hour. We also need to be connected to a network in order to get the lottery results and also make our purchase after we're notified. We also know about the approximate time that the results will be available, around 10 a.m. for the first drawing and around 3 p.m. for the second drawing, so our choice should be able to accommodate that schedule. And we also need this alert to allow us to launch additional work for our app, the work that fetches the show artwork and delivers it to our notification and also notifies us. So just as before, we have several possibilities for the various combinations of APIs that we can use in this scenario. One option is Alarm Manager and Work Manager, so potentially setting an alarm for the 10 a.m. drawing and the 3 p.m. drawing, and then running an expedited worker, a foreground service, and finally, Firebase Cloud Messaging and WorkManager, so receiving a message to trigger an expedited worker. So to skip ahead for this feature, it's a little dim there, but we're going to opt for the third option, which is an expedited worker and FCM. And this is the best choice because it makes sure that our work runs at the right time. But let's briefly also go through the other options and review exactly why we're choosing option 3. So starting with Alarm Manager, first there's a small hurdle that immediately makes this just a bit more inconvenient. We would want to use an exact alarm since an inexact alarm can run up to an hour or even more after the designated trigger time that we set. Beginning with Android 12, setting an exact alarm requires that the user grants the set exact alarm permission. And we have options here. We could definitely try to reason with the user and provide some justification for why we need this permission. And there's a good chance that they might grant it if they actually do care about claiming these tickets in time. But it's still a risk. A couple of other issues. If the alarm fires and there's no network, then it won't reschedule for us. We'd need to write some extra logic. And as someone who has entered a lot of these lotteries and has also won a lot of these lotteries, sometimes you're notified of a win as early as 9:15, so well before 10, and then sometimes as late as 3:30, so 30 minutes after that 3 p.m. assumed time. So this means that we can't actually just set a single alarm. We would actually probably need to fire multiple alarms over the span of like 20 to 40 minutes and hope that at some point in that window, the results are released, which is very bad for battery. And before we move on to the next slide, a caveat that high priority FCMs and foreground services also contribute to battery drain, but it's a balance of making sure that you respect the system and your users by choosing the most appropriate solution. So if you need expedited work or you need a foreground service, use it, but don't opt for those choices if you can also use an alternative that is better for battery. So to dive into why we're not using a foreground service, there's a few reasons here as well. First, we can't launch a foreground service from the background. So ideally, we would have the foreground service start as the result of some sort of user action, which is kind of impractical in this situation, or in the case of the lottery, due to the results being released. But again, that would require it to launch from the background. There's also no network constraint with the foreground service, which we mentioned earlier as well. And foreground services are best for ongoing tasks, but that's not really what we need in this scenario. We just need to know that we've won, figure out for which show, and then launch some additional work that lets us respond accordingly. So in theory, if we were to use a foreground service, we'd probably want to schedule it start it when we enter the lottery, and then keep it running to receive the results, which is not a good use of a foreground service. So another possibility, before I explain the last option that you might be thinking of, is instead of using WorkManager to run this work, why not use a coroutine instead? And the answer to that is that a coroutine is susceptible to being killed by the system once the high priority FCM's on message received method returns. And one of the benefits of WorkManager is guaranteed execution, even if the system does decide to defer that work. So going back to WorkManager and FCM, I mentioned that we do know the approximate times of the lottery. And so if we were to schedule a regular one-time worker with a delay, so not an expedited worker and not using FCM at all, then we could attempt to try to get our work to run as close to the results time as the system will allow. But again, because that time varies, and that was also the issue with Alarm Manager, we have to combine our work with an FCM to make sure that our work runs as a result of the actual lottery release. So here is how we will tackle this. We'll use an FCM and an expedited worker, which is a type of work that should run immediately and will execute as soon as the system allows. And we have to actually use an expedited worker here because we want to ensure that the FCM gets processed as immediately as possible. So very simple diagram showing the flow. But basically, the backend releases the lottery results, which triggers a high priority FCM. And a high priority FCM versus a normal priority FCM is the right choice in this case because a normal priority FCM can be affected by doze mode, and it also should be delivered when the device's screen is on. Because we don't know if the device's screen is on, and we don't know if we're in doze, a high priority message will attempt to deliver this message immediately, which is what we need. And so this wakes the app up when the message is delivered. And the onMessageReceived method from the FCM schedules the expedited work, which runs as soon as the system allows, fetches our artwork for the notification, and displays it in a notification that alerts us to the win. If you want to know more about how to use Firebase Cloud Messaging, I recommend reading this blog post. It covers some of the trade-offs between normal and high priority messages, how to test FCMs in doze mode, and also considerations when using WorkManager with FCMs. So let's dive into some code here. So here's the code showing our expedited worker. We implement getForegroundInfo, which we need to do in order to allow WorkManager to support versions of Android that are older than Android 12, where it runs a foreground service to execute this work. We pass this method to setForeground in doWork, which will create a notification if a foreground service is needed on those earlier versions. This is not to be confused with the notification that we want to display to our users with the actual lottery results. I have omitted that here, but that's a notification that will display across every version of Android. And then when we go to schedule our work, by calling setExpedited, we signal to the system that this work is critical and that it needs to run as soon as these constraints are met. And this will give us the best choice of running within our desired window, because with normal work, there is a chance that it could get deferred by the system. And as I mentioned before, our constraints, we need internet to get the results and to also buy the tickets. So instead of constantly checking to see if we're connected in our time window, we can specify the network connectivity constraints. Okay, so here's a recap of what we covered in this section. Some trade-offs with using Alarm Manager, and also how to use an FCM with expedited work. Okay, our final features are price drops and seat availability. They're very similar, so we're going to tackle these features as one. With both of these features, we want our app to be able to track changes, mostly when the app is in the background and our users aren't interacting with it. Until now, our other features have been relatively contained to short bursts of work that don't require a lot of resources over time necessarily. But now our app will be polling in the background periodically for all shows that are currently showing. And we've also added 2 constraints that we want to use here, connected network and battery not low, which we haven't used yet, but it's just making sure that when we run our work, the user's battery is not low, because we want to be a good citizen. So don't spend too much time on this. This is buggy code, but we'll get to that later. But basic implementation of the doWork method of these 2 workers. So that was price drop worker, and this is the availability worker. So I'm going to schedule them as periodic workers to run once every hour and to check for new seats or check for price decreases. In terms of constraints, I mentioned those. We're going to require a connected network and battery not low. They're not on this slide, but that's what we have there in that constraints value. And I also have to note, before we get into this, that a much better version of this feature here would be to do what we did in our previous feature, the lottery feature, where we run our work as the result of an FCM. So that way we could make sure that we actually only run this work to respond to actual changes instead of just running this once every hour. But this is just for the purposes of this talk. So we're going to go with this implementation. Okay, fast forward 3 days. After a couple of days, our periodic workers have stopped running as frequently. We haven't seen a new price drop or any new seats, even though we know from other sites that there have definitely been changes. So we have a couple of options for figuring out what went wrong here. Before I dive into this, though, one thing that we're not going to cover is how to debug app power drain. And debugging app power drain isn't just about avoiding bad user experiences. It's also about being a good citizen on your user's device. And an app that drains the battery aggressively can have severe consequences, so not just impacting your user's experience and their device, but also affecting your app's visibility on the Play Store. So I highly recommend, if this sounds important, to check out my colleague Alice's talk tomorrow on this exact subject. It's called Powering Up Your App Performance and Stability Using App Vitals. Our app's issue so far is not excessive power drain though, so let's try to figure out what went wrong. So the most obvious issue might be our constraints, and that's usually a good place to start. You'll recall that we set a constraint for both of our workers to require that the device's battery isn't low, and also to require internet connectivity. So there are a couple ways that we can check constraints. We're not going to go through each one in that much depth, but to start, here is one option. This ADB command will return a list of jobs along with the associated status of the constraints. Okay, a lot of text on the screen there, but this is an example of the ADB dumpsys job scheduler output, and this will work on Android 6 and higher. So when you run this command, it'll return a lot of eligible workers and jobs. So to get this one specifically, I did also delete a lot of text here, but to get it, you search for your package name, because you'll also see here that availability worker, price drop worker, they're not named here. They're referred to as system job service. So our package name is the best way to find this. And that is because WorkManager is built on top of JobScheduler for many versions of Android, and it uses JobScheduler under the hood. So that's why this command, which is ADB dumpsys JobScheduler, works for both JobScheduler and WorkManager. Okay, so on this slide, I've removed a lot of the output from that previous one, just to make sure it fits and that it's kind of big. But you'll notice I've bolded the constraints that we set: battery not low and connectivity. And you can also see in this output that we do have an unsatisfied constraint. It's not one of the constraints that we set though. And this is actually alerting us of what our issue is, but we will get back to this soon. Another option for checking constraints is the background task inspector, which is available in Android Studio. And Alice's talk tomorrow will also cover the background task inspectors, so I recommend attending that talk or watching that talk if you want to see this in more detail. The background task inspector is a tool that lets us visualize our work and can also give us some insights into a worker's execution, constraints, and also things like retries. I'm going to zoom in a second, but here's a screenshot of our work in the background task inspector. We have two constraints that are listed here, which you'll see when I zoom in: connected network and battery not low. And we know that both of those are met. And you can also use the background task inspector to debug wake locks, which Alice's talk tomorrow will also cover. So here's a zoomed in view of some of the information that the background task inspector will provide. And beyond the background task inspector, we also added a few things in our code to help us debug issues like this as well. So to help us check the status of our work and also get a better idea of why it was stopped, in our code, we also called workinfo.getStopReason when we scheduled our work. And if you want to use this with JobScheduler, you would call jobparameters.getStopReason. And this will allow us to see why a job or work might have been stopped. There are a lot of different values that can be returned in this situation and will also guide us to what to tackle next. Here, I'm also just having the values show up in the logs, but if you wanted to use this, you could also make it so it gets uploaded somewhere. So in addition to the background task inspector and getStopReason, we're also able to check the status of our work by requesting diagnostics from WorkManager using this command at the bottom there, which is just request diagnostics and your package name. And so in our scenario, we ended up using workinfo getStopReason, which informed us of StopReason quota. And StopReason quota points to our app having exhausted the resources that have been allotted to it by the system. I also want to point out that there are 3 ways in which work might be limited by the system. There's device state, so if the device is charging, if the screen is off, if it's on, if doze mode is active. App state, so is the app running a foreground service? Has the user manually restricted battery, things like that. And finally, app standby buckets, which I mentioned earlier at the beginning of the talk, but they're categories that the system places your app in, depending on how often your app has been used. So skipping ahead to app standby buckets, we're able to check what standby bucket our app is currently in. And also see if we might be outside of that active bucket, which allots us up to 20 minutes in a rolling 60-minute period on Android 16. So to do this, we call get app standby bucket in our app, and then we run this ADB command, which is actually very small on the screen. Okay, I've already run this command, and any value over 10 means that we actually aren't in the active bucket and that we are being affected by system restrictions. So I ran this and we got 45, which is way higher than 10 and means that we're in the restricted bucket. Apps can be placed in the restricted bucket for a couple of reasons. One, if a user hasn't interacted with the app for many days, or if the app is consuming a lot of system resources. And I also want to mention that you can test your app across different app standby buckets to see how it will behave. And this is a really good best practice because you can't actually influence your app standby bucket unless you're exhausting system resources, as I am. And the standby bucket that your app is assigned to after some inactivity can actually vary across different phone manufacturers. And if you want to see more about app standby buckets and the other power management resource limits that I mentioned, you can see them on this page. Okay. I don't think that our work is intensive enough that we should be hitting quota like this. We have, however, depleted our quota. And knowing that we're in the restricted bucket, along with having depleted quota, points to us having a bug in our code. So, as I said, this is intentionally buggy. So don't do this. Don't take a picture of it. But essentially, the URL that we are attempting to get changes from is actually unresponsive. And this is what's causing quota to be depleted. We keep retrying this URL and it never times out. We also probably should have never gotten to this point. There are many ways that we could have avoided this that we won't cover in detail now, but briefly, we could have written tests. We could have used WorkManager's testing library. If the URL was unresponsive, we could have also have set a max number of retries. You'll see that we call result retry a lot, but we never set a max number of those. And WorkManager actually tries to help a bit with this, where it has an exponential backoff policy for retries. By default, it's exponential, but you can also set it manually to be linear, and that just means that if it's exponential, it'll increase the amount of time between each retry. So if it tries after 30 seconds, it'll then try again after 60 and then 90 and keep going. And there is a max amount of time that you can hit. And so even though the amount of time between each one of our retries grows, we still have exhausted the quota before that max was hit. We could have also, instead of result retry, returned result failure to signal to WorkManager not to retry the work and that the URL doesn't exist. Here's a recap of what we covered in this section: debugging constraints, how to check the status of your work, and also app standby bucket resource limits. And that's our app, coming soon to a Play Store near you. Thank you. I'm around if there's any questions, and the Google team also has some swag to give out if you find us later.